So it's my great pleasure to welcome the first speaker, Michael Wheeler, who is a mathematical physicist at the University of Melbourne. We've heard a little bit about asymmetric exclusion processes in previous speakers we've had at the workshop, but I'm very interested in hearing more about them, and in particular the recent work that the group in Melbourne has been doing on this subject, which leads to, in one thread at least, my favorite equations. So without further ado, let me invite Michael to launch into his talk, and thank you very much.
And thanks very much, Nalini, for the introduction, and thank you to the organizers for the kind invitation to speak here. So yeah, indeed, I will be talking about the asymmetric simple exclusion process. And basically the most simple type of problem that you try to solve within this process, which is to compute its transition probabilities. So I'm going to start off with essentially some review about the ASEP, because I realize that it's quite a diverse audience here. So perhaps not everyone is so familiar with the basic material. So I wanted to spend a little time just motivating and setting up things. So asymmetric simple exclusion process. So the first thing you need to know about it is that it is a Markovian process. So there is some degree of randomness in this system, and essentially what it is a system of particles which are hopping around in one dimension. Okay, so these particles, they're either hopping towards the left, as indicated here, or they're hopping towards the right. But there is an exclusion rule which prevents a neighboring particle hopping on top of another one here. So for example, this hop would be forbidden. And typically what you want to do is set it up so that the hops are actually asymmetric. So they're happening with different rates. And conventionally, what we choose is the left rate to be equal to q and the right rate to be equal to 1. Now, mathematically, what this means is each of these particles, you should think of it as having 2 alarm clocks which are attached to it. And these alarm clocks are ringing randomly, and the waiting time before you have a ring is given by the exponential distribution. And the parameter that appears in the exponential distribution is precisely this q here for the left clock and this 1 here for the right clock. And in practice, what we typically do is take q to be somewhere between 0 and 1. So typically speaking, there will be some sort of drift in this direction as time evolves. Okay, so that's the system. And the first thing that should be mentioned about this system is that it has a very close relationship with another very classical object in integrability, which is the XXE Heisenberg spin chain. So in fact, if you look at the Hamiltonian of the XXE Heisenberg spin chain, there is a similarity transformation, some conjugation of this Hamiltonian, which actually maps it to the generator of the ASEP. So there's really a very close relationship between the ASEP and integrability from the very get-go. So the problem that we're going to be interested in, and I'll say a little bit about how this works in the model that I've just introduced, the problem is to compute transition probabilities. So we'd like to know, if the system is in a certain state initially, after time t has evolved, what is the probability of finding it in some different state? And so in order to sort of make progress with that kind of question, you like to have some differential equation which actually governs the evolution of these probabilities. And this is referred to as the master equation if you're talking to physicists, but if you're talking to probabilists or mathematicians, then they might refer to this as the Kolmogorov-Ford's equation. Okay, so let's try to formulate this master equation. So the first thing we'll need is some way to actually label states within our system. And so the labeling that I'm going to use is going to be a signature. So for me, a signature is just going to be a sequence here of ordered integers. So each one of these mu i's is in the integers, and they're strictly increasing here. So that's in the following. Whenever I refer to something as being strict, that's what I mean. Just that you have to have these strict inequalities. Okay. And this mu I, you can think of this as being the coordinate of the ith leftmost particle. Okay, so I'm working with a system here which is left finite. So that is to say that I can have many particles to the right, but as I go out towards the left, eventually there will be a leftmost one. And beyond this, I'll just have empty space. Okay, so that's going to be my labeling. And we will let this symbol here denote the probability that if I initialize the system in state mu prime, after time t has evolved, the system will be in the state mu. Okay, so that's our basic quantity in question, is transition probability. So the transition probability satisfies this master equation, which I mentioned above. And it's actually very easy to just derive the master equation from first principles. So I think it's perhaps instructive to look at that here. So what we will do is we'll essentially work with a small time interval delta t now. And I'll look at the probability that at time t plus delta t, I'm living in this state mu here. Okay, so what can I say about that probability? So what I would like to do is express the probability of being in that state here at this time. I would like to express it in terms of the probability of either being in that state or not at time t. So essentially, I want to see how this probability changes as I shift by this delta t here. And if you think about it, there's essentially two ways that you can end up in this state here at this particular time. So the first way is that at time t, you're already in that state. And then in the time interval delta t, you actually remain in the state. Okay, so that's the first way. And that's represented by what's written here. Okay, so indeed, here's probability of being in that state at time t. And then this quantity here looks a little more complicated, but essentially what we're computing here is just the probability that you remain in that state during this small time interval, delta t. Okay, so what's going on here? So I'm actually computing this quantity here. So this m here, this is the generator of the process. So this is the matrix that encodes all of those hopping rates that I mentioned at the start of the talk. So this thing here is just a very sparse matrix. So it consists mainly of zeros, but the non-zero entries are either going to be 1 or q, depending on whether those two states here are related via a left hop or via a right hop. So this is just a matrix consisting of mostly zeros, but some ones and q's as well. And so I take that thing and I multiply by this time interval here. And so what this ends up computing now is actually the probability of going from the state mu to some other state nu, which is different from the original one. So if I take 1 minus this, then I'm actually just computing the probability of staying in that state. Okay. And the other way that I can end up in this state at this time here is basically if I start in a different state, and then during the time interval delta t, I actually transition into it. And so that's represented by this term here. Okay, so here is indeed the probability of being in some other state, nu, which is different from the one that we're interested in. And then the remaining piece of this term here is again working out for us the probability of actually transitioning into that state during this time interval. So I have all of that, and then I have some higher order terms in delta t, which we can essentially ignore. Okay, so that's basically how you do this from first principles. And now it's very easy to actually take the limits now where delta t goes to 0. So in that case, we'll sort of transition back to continuous time, and we'll end up getting a differential equation. So let's have a look how this works. So the first thing we should do is we should actually take this sum here. So this sum was appearing in the first term that I had just above. So just here, I had this sum over all states nu, which are not equal to the one that I'm interested in. And so that thing there, I'll just define this to be this quantity here. So essentially the generator, if you like, where both of the components are the same. Okay, so with that definition, you can actually rewrite the equation and you end up getting this now. And having a look at this, now we actually very easily see that we can just turn this into a differential equation. So I just take the difference between these two things here and I divide by delta t, and I take delta t to 0, and this is just the classical definition of the derivative. And so I now have that ddt of our probability is given by this right-hand side here. Okay, so this is the master equation, or if you prefer, this is the Kolmogorov-Forwards equation. Okay. So yeah, please feel free to interrupt with any questions that you may have. Okay. So at this point, this is an equation that governs these transition probabilities, but it doesn't really tell you anything about them explicitly. So of course you can solve this equation formally as, basically taking the exponential of the generator. So that's a formal solution, but it doesn't really give you much information about these probabilities explicitly. And indeed, if you want to do any kind of asymptotic analysis, you're going to need a more concrete formula. So this takes me to the work of Tracy and Widom from 2008. And so in 2008, Tracy and Widom, they actually obtained an explicit integral formula for these transition probabilities. And so I've just basically copied down their result here using the notation that I'll be using throughout the talk. So, okay, so they considered the case actually where the number of particles that you have in the system is finite. So in this case, we don't even work in terms of these left finite signatures, we just work in terms of finite signatures. So I have two of them, and I'm looking for this transition probability that if I start off in state mu, I'll end up in state nu at time t. And this is the formula. So I have this n-fold contour integral, and I have, well, essentially an integrand which is relatively simple. So there is some exponential factor here, which you definitely expect to see, given that we're dealing with a continuous time Markov process. So this is really something that should definitely show up. But then really the important information is encoded in terms of these functions here. So these are some rational functions that depend on these two signatures. Okay, so the first one looks like this. So it's just this rational function here with the exponent given by the position of the ith particle. And the second one is a little more complicated. And indeed, for people who are familiar with beta ansatz, this is really a beta ansatz type formula, sort of formula that you see when you compute the wave functions of the XXC spin chain. And again, it's not so surprising that that should show up, given that this model is related to XXZ spin chain in the first instance. Okay, so that's the formula. And you know, it's quite amazing that you get such a complicated formula for such a simple model. I mean, really, we're dealing with a very bare bones model, just particles hopping in one dimension, and you know, the hopping rates are basically the simplest thing that they could be. There's an exclusion rule to prevent particles hopping on top of each other. It's as simple as it could possibly be, but already there is a very non-trivial formula here for these transition probabilities. Okay. So the way that they prove this, so I don't actually know how they arrived at this formula a priori, but once you have the formula written down, you can just check that it satisfies the master equation. So it has the correct time evolution, and you can check that it satisfies the correct initial condition. So they did this in their paper. So checking that it satisfies the differential equation, this is actually not so difficult because the differentiation with respect to time is purely contained in this factor here. So you can actually just differentiate inside of the integral, and this is very easily differentiated. And then you can just check actually that the master equation holds on the integrand itself. So you don't even need to have the integrals in order for the master equation to be satisfied. But the difficult part is checking that this thing satisfies the correct initial condition. So that's actually really difficult. So the initial condition, of course, is that if I take time to 0 here, I will expect that that transition probability will just coalesce to the delta function. Okay, so I'll need to have 1 if the two compositions are equal, and if they're different, then I expect to get 0. And that's a much harder thing to actually check for that integral formula. So in order to do that, you essentially need some sort of orthogonality property of these two functions that appear inside of the integrand. Okay. So that was their formula. And the reason why they were interested in computing these transition probabilities in the first place is they were interested in doing asymptotics. So studying asymptotic behavior of the ASEP. So basically the case where the number of particles goes to infinity.
Michael, can I just ask a quick question?
Yes.
When you mentioned the Tracy Widom paper, they have many papers. Do you mean the original big one of 2004?
No, I was referring to...
Oh, the 2008, I see.
2008, yeah, I think from that year they have 3 papers.
Right, okay.
This is in the first one.
Okay, thank you.
Yeah, so indeed, in that first paper, they derived this formula, and then essentially in the subsequent 2 papers, they were looking at asymptotics. And that's where they found this link to something else that bears their name, which is the Tracy Widom distribution. Okay, so I'll say a little bit about that here. So of course, the first thing to mention is this transition probability here. What is it actually? So in probabilistic terms, this is a joint probability distribution because you're dealing with essentially m particles now, and you're asking what is the probability that particle 1 is here, particle 2 is here, etc., etc. So it's a joint probability distribution, and it's rather complicated. So in order to be able to do something meaningful, what you would typically do is restrict to certain marginals. So for example, I might just restrict to the first particle. What is the position of the first particle, and just forget about where the remaining particles are. That's a typical marginal that you might be interested in. And something else that I haven't said anything about so far is what actual initial condition should you choose here. So how should you initialize your system such that you get some interesting behavior, or such that you can actually compute in the first place. Okay, so that's that's what I'm going to talk about now. So the initial condition that is perhaps the simplest one to choose is to take this mu here to be just 1, 2, 3, 4, just all of the natural numbers. So in other words, that means I have initially particles which are packed together at all of the positive integer sites, and then everywhere else I just have holes. Okay, and so this in the literature this is referred to as step initial conditions, or if you prefer, this is something like the Fermi sea or the vacuum of a Maya diagram. There are many different names for what this is. So these are the step initial conditions, and these are the conditions that Tracy and Widom focused on in their work. And the marginal that they were interested in, which is this thing I've denoted here, was the following. So this xm here, this is the position of the mth particle from the left at time t. Okay, so this is really a random variable now, and they were interested in the probability that this thing here is less than or equal to s, where s is just some real parameter, if you like. So this is nothing but the cumulative distribution function for this random variable here. And in terms of the notation that we've been using, what it means is I should just sum over all states nu with this probability here, and I filter out, so I get rid of all of the states such that the mth particle is located, somewhere to the left of this position here. Okay, so that's the definition of this. So they took that quantity and they did some scaling. So this is the result. So they take the position of the mth particle, and they also scale time now linearly with respect to m. Okay, so this is the time parameter here. There is some additional scaling factor alpha. There's another scaling factor beta here, and what they're doing here is just subtracting off this linear term here. So it was known actually from work of Liggett that if you look at the asymptotic behavior of this mth particle, it actually sort of has a linear drift as m goes to infinity. Okay, so it was expected from earlier work that if you subtract off this linear term here, that essentially describes the law of this mth particle. Okay, so that was expected, but then there is the computation to the next order in m, and it turns out to the next order in m, the correction that you get is actually of the order m to the 1/3. And this is rather significant in this subject because random variables that have this particular correction m to 1/3 are said to live in the KPZ universality class, which is distinct from the Gaussian universality class, where you have like central limit theorem, all of these classical results. So they looked at this probability here, and they proved that actually this probability is given by the Tracy Widom distribution. So for people who haven't seen it before, Tracy Widom distribution, it actually has a similar definition to, it looks very similar to what I just wrote up here. But what you do now is you take the nth eigenvalue of a random n by n emission matrix, and again you subtract off the law. So the eigenvalues of a n by n emission matrix, they satisfy what's called the Wigner's semicircle law. So if you look at a histogram of the eigenvalues, essentially forms a semicircle, and the radius of that thing is actually given by this. So the largest one is situated all the way on the radius of that semicircle. So if I subtract off this thing here, and also have this factor here that tells me the fluctuations, that thing there is precisely the definition of the FG. Okay, so that was their result. And in fact, their result was also expected in some sense, since this had been done several years earlier by Johansson in the case where Q is equal to 0. And this Q is equal to 0 is referred to as ASEP for totally asymmetric simple exclusion process. Okay, so that's a very brief summary of what is known about the ASEP and some of its scaling behavior. Okay, so I should probably carry on with the rest of the talk. So what we have been interested in recently, so with collaborators in Melbourne, is to essentially extend this to the multi-species case. So that's where you look at an ASEP that actually has different colored particles now. So multi-species ASEP is a situation where you again have these particles in one dimension, but now they all have distinct colors. And so what this facilitates in particular is neighboring particles now, they can actually exchange. So normally when you have neighboring particles in the ASEP, there's no chance to hop because of the exclusion rule. But now when they actually have different colors, they will actually exchange with some rate, which is either Q or 1, depending on the relative ordering of these colors here. So each one of these colors is just a natural number that I assign to the particles. And I assume that all of the particles have a different number. So they're all distinguishable. Okay. So this is the multi-species ASEP. I've given the sort of formal definition here, but I think there's no point in trying to stress this here. But as I said, it's essentially exactly the same dynamics as for the ASEP, with the inclusion of the fact that you can now have this exchange between neighboring particles. And it's motivated algebraically as well, in the sense that the original ASEP, this is related to this quantum group. So I take UQ over fine SL2. There is some algebraic structure that underlies the ASEP, and the sort of the highest level of that algebraic structure is this quantum group. And so the natural extension of this is to replace this by SLN. Maybe I should say SLN plus 1. So if you do that, then the corresponding process is actually this colored process here. Okay, so in a sense, the multi-species ASEP is the natural lift from SL2 up to SN. Okay. So what we would like to do is, within this multi-species ASEP, we would like to play exactly the same game. So we would like to compute transition probabilities. If I start off in some state, what is the probability of getting to a different state? And once one has explicit formulas for those transition probabilities, you would like also to be able to, say something meaningfully in terms of asymptotics. So, is there some interesting marginal that I can study within the system? What is the location of one of those particles? Is there some scaling I can do of this? Can I recover Tracy Widom distribution? These are all questions that you can ask within this multi-species ASEP. And to date, there is really very little results asymptotically in these directions. Okay, so I'm going to talk about how you can actually derive a formula for the transition probabilities for this multi-species ASEP, and the tools that you need in order to do this are actually these vertex models that are based on, again, this quantum group here. Okay, so now I'm going to change the setting slightly and talk about a two-dimensional integrable model, which is this one here. So this is actually a very natural higher rank generalization of the 6-vertex model. So it's a model where you have vertices of the form here, and the vertex is decorated by these four labels that take values from 0 up to n. And furthermore, it depends on two parameters, x and y, and in particular, it depends actually on their ratio, which I denote by z. Okay. So whenever you see a vertex like this, you should just think that this is some complex weight, actually. So this thing here is literally just a complex number, or if you want to do probability, it will be a real number. So whenever you see this, just think this is a number. This is something that I can just compute using the information that I'm given here. Okay, so the first thing is that number is equal to 0 unless the colors that come in and leave satisfy this conservation property. So basically, if I look at the union of those two colors there, it has to be equal to the union of these two colors. So whatever goes in has to go out. And for all of the cases where you do have that conservation, you can actually write down the weights explicitly. And this is what they look like in this table here. Okay, so you see they depend on this z, which is the ratio of those two variables. And they also depend on q, which is exactly the same q which appears in our ASEP. Okay. And so there are 5 different types of vertex here. So I won't say too much about these. But there is one thing about this particular parameterization of the weights, which is very nice. And that is, if I look at this pair of vertices here and here, if I actually add up those two weights, they sum to 1. And likewise, if I look at this pair here, add them up, they also sum to 1. And so this sum to unity property actually allows us to use this model now to do probability. So that's explained here. So it has this sum to unity property. So for all I and j, so these are the incoming colors. So I fix these to whatever choice I want, and then I sum over the possible outgoing states. And so no matter how I fix these, whenever I compute the sum, I always get 1. So that actually means that we can view this thing here as being a probability distribution that we actually assign now to these vertices. And you can actually use it to construct some sort of 2-dimensional Markov processes that live in the plane now. So you simply start off from the quadrant, and you start sampling vertices using this stochastic rule, and you just gradually fill out the vertices in your quadrant, and you get some sort of random configuration of vertices. Okay. And another thing which I won't say anything about, but which of course is classical and much older than the field that I'm talking about, and that is the fact that this model satisfies the Yang-Baxter equation. So there is some integrability underlying this vertex model. Okay. So the reason why we're interested in this vertex model is you can actually use it to construct essentially a discrete time analog of the ASEP. So there's going to be some sort of 2-dimensional setting now with like a discrete time, and there'll be some limit that we can take such that we actually reduce to the continuous time ASEP. And so the procedure for doing that is this transfer matrix here. Okay, so I define a partition function now that lives in the model that I'm interested in. So here is my partition function.
Michael, you have 5 minutes left of talk time if you want to allow 10 minutes for questions. Okay, yeah.
I'll try to go for 7 minutes, something like that. Yeah.
That's fine.
Oh, thank you. Yeah. All right, so on the left and the right boundaries, I take all of the states just to be zeros. And so what's happening actually is all of my colors are entering from the bottom and they're leaving at the top. Okay, so I might have something like this. So here is a particle of color I, and here is a particle of color J, and they're going to make their way to the top and leave somewhere at the top. So this is I, this is J. All right, so the rule is color I is going to enter at position mu I. So mu I will tell you where color I is going to enter along here, and it will then exit at position mu I. So when I have those two compositions, they'll actually tell me basically the coordinates where all of the particles enter and leave. And what you have to do is now compute all possible ways for the particles to get from A to B, work out that partition function, which is going to be some complicated rational function in general. And that thing is the definition of this G here. Okay. So as I said, is there's a limit that you can take such that you recover the ASEP on the other side. Okay, so what I do is I take all of these row parameters, I take them to be very close to 1. So they're equal to 1 minus epsilon times some constant here, where epsilon is small. And if I look at the weights under this particular choice of the variable, I end up with the weights that are in this table here. And here I have truncated the form of the weights up to order epsilon. So that's what I have. And basically now you can look at the model as shown here. And what you will find is that in general, the vertices will overwhelmingly take this form here, or they'll take this form or this one. These are the ones that have overwhelming probability to occur. And these constitute the sort of order epsilon events that happen very, very seldom. And if you actually look at the ones that happen with the large probability, they're the ones where the particles tend to zigzag. So here, there's sort of the particles are doing this kind of motion, right? And it's the same here. So with overwhelming probability, if you go back to the picture that we just had before, if I work in this particular regime of the weights, the particles will tend to want to do this. So there is some sort of drift to the left, but overwhelmingly, they just want to zigzag. And it will occasionally happen that instead of zigzagging, and this happens with probability epsilon, this guy will actually take a step straight up and then just continuing zigzagging like this. Or the other small probability event is where a particle just steps across like this by one step. And so actually those cases where it goes straight up or straight across, this will correspond now to the actual hopping events within the ASEP. So I don't really have time to explain this, but here is the formula. So there is some limit to G such that you recover the ASEP when you take this scaling. Okay, so in the remaining 2 minutes, I will say something about the spectral decomposition of this G. So the whole point of these Gs is there's actually a very nice spectral theory behind them. So you can actually meaningfully get a formula for these things, which sort of mirrors the spectral decomposition of a matrix in terms of its eigenvectors. So, okay. Probably I won't have time to mention this too much. So there is some other family of functions F, and in a nutshell, these play the role of the eigenvectors of the G. So you can think of them as being the eigenvectors. And the reason why they can be thought of as the eigenvectors is there is this equation here, which is sometimes referred to as a skew-Cauchy summation identity. And this really casts the Fs as being like the components of the eigenvectors of the G. And in fact, you see here, you actually have infinitely many eigenvectors because they depend on this family of parameters, x's, which can be whatever you want. So you actually have an infinite family of eigenvectors of this matrix, which of course, this matrix is also infinite dimensional. Okay. And furthermore, these Fs, they have a nice orthogonality property. So there is some integrals that you can perform, and yeah, essentially these Fs end up being self-orthogonal with respect to this integration. And so basically combining these two facts, the previous eigenvector equation and this orthogonality, you can actually get an explicit integral formula for the G. And so on the final slide, I will show it. So here it is. So the G can be written in this form here. And you can then go ahead and take the limit from this G to the ASEP that I showed previously, and you end up with an explicit formula for the transition probability of the multi-species ASEP in terms of these Fs. Now, I haven't said too much about these rational functions F, but they have, there are some explicit formulas available for them. So this is actually a rather explicit formula for these transition probabilities. And what we would like to do in future work, and we already made some steps towards this in the paper with Gier and William Mead, what we would like to do is now perform suitable asymptotic analysis of this formula in a similar vein to the work of Tracy and Widom from 2008. So yeah, sorry I was a bit rushed at the end, but I'll stop there and take questions.
Thank you very much, Michael, for a great talk. Are there any comments or questions?
Thanks for the talk. It was very nice. My question goes a while back, but maybe it refers to the final formula as well. So the Tracy Widom result in the end did not depend on Q, I suppose, right? Because the GUE does not depend on any parameter.
Yeah.
So where did the Q go? And I suppose it's hidden in this beta and the drift rate. So is there a formula for the beta in terms of Q?
Yeah, that's right.
Then maybe the next question is, do you also expect a universal result for this more complicated process that you're studying?
Okay, so to answer your first question, indeed, the Q is sort of buried in terms of these parameters here. So they in their paper they give very explicit formulas. Yeah, they give very explicit formulas for these. Yeah, I just wanted to avoid it here because they're a little bit ugly for the purposes. And your second question, yeah. So the challenge actually in the multi-species case is to actually come up with, in the first instance, a suitable observable, because it's not even clear actually what you should be looking at before you try and do any scaling. So, at this stage, what we have is a formula for these this joint distribution. So we have this explicit formula for the transition probabilities, but then you have to restrict to some marginal. You have to restrict to looking at one of the particles, or so you have to measure something. So the first challenge is identifying what you would like to measure. And then the second challenge is, actually being able to explicitly do the asymptotics. So there is not much that has been done there, but actually what we did do in the paper with Jan and Will, we looked at sort of a very particular case of what I described here, and that's the case where the particles totally reverse their ordering after this time interval has evolved here. So, I might start off with particle 1 here, particle 2 here, and then maybe particle 3. And what we looked at is the situation where they totally reverse their ordering like this. And in this setting where the particles totally reverse their ordering, the formula actually simplifies a lot. So you actually get some explicit formulas now for these probabilities. And there, we believe that you can actually do sort of explicit asymptotic analysis. So there is definitely some evidence to suggest that this is the sort of the natural candidate to look at in the higher ranked case.
Very interesting. Was there another question? Yes, Elfno.
About the G mu nu, it is a permutation rational functions matrix, basically. Would it be possible to think of the decomposition of the permutation matrices and the rational function? Would that help for calculations? Would it be possible to do that, or is it too complex to do that?
Sorry, I'm not sure I've understood the question.
It is not like a spectral decomposition. I'm thinking like a matrix decomposition, because if you can have the permutation matrix acting from the left-hand side, changing the rows, and acting from the right-hand side will change the columns. If we can separate the permutations, would it be possible to obtain a nice rational functions matrix in the middle? Would that be helping for the calculations?
I would expect not. Yeah, I mean this G is a rather complicated object. I don't think so. I don't think that this sort of approach would be helpful for including the G. So it's true that what I described here is not a true spectral decomposition. It's actually somewhat unusual because you have, on the one hand, you have this thing is the matrix elements of some infinite dimensional matrix, right? Which is, I'm labeling the two the row and the column using this mu and nu. But in turn, not only do you have these the matrix elements, but you also have the family of parameters here. And really the decomposition is actually happening with respect to these parameters here, rather than with respect to the matrix itself. So it's kind of a spectral decomposition with respect to these variables here. You could really think of this integral in a sense like this one. In a sense, this is like the summation. It's kind of like spectral decomposition. You would expect to do something, something like this, summing over mu and u, right? And here, that's the role of the summation is really being played by the integration somehow.
But it does show the complexity of the problem. Yes.
Yeah. Thank you very much.
So maybe I'll sneak in a question, which is, you talked about the Tracy Widom distribution that you get as a limit. And of course, the Tracy Widom distributions relate to my favorite functions, which solve the Punleve equations. Is there a Punleve equation hidden here? Maybe a discrete Punleve equation?
You mean already at the level of the G's, or?
Yeah.
Yeah, that's a good question.
The reason I ask is that there is also some work by Elsa Kniesel, who was a student of Borodin's, who looked at certain types of probability distributions that have the parameter Q in them. I'm not sure whether that's actually related to your situation, but that does lead to Q orthogonal polynomials and to Q Punleve equations of certain kinds.
Yeah, so definitely the Q in question there is morally speaking the same one.
Yeah.
Here, yes, that's correct.
Yeah.
It's a reasonable suggestion to hope for some sort of discrete Punleve.
I'm always hopeful.
Yeah, there is definitely some chance of something like this. Yes.
Right. Thank you. Let's thank Michael for a wonderful talk.